Okay, so we have another discussion which is the strain. Strain is the elongation per unit length. So strain is what we also call elongation, or this is also what we call deformation. So when loads are applied to a body, some deformation will occur, resulting to a change in dimension. So strain is unitless. So strain is equivalent to change in length, delta L, over original length. So simplest formula is change in length, or the delta L over L. So if this is our object, this is the original length of our object, and if there's already an applied deformation, this is now the change in our length. So there are also types of strains. There are normal or direct strain. So the same, this is still referring to the tensile and compressive stresses. So we also have what we call the modulus of elasticity, constant of proportionality, slope of a line in elastic range. It is also known as the elastic modulus, the tensile modulus, or Young's modulus. Is a number that measures an object or substance's resistance to being deformed elastically. Hooke's law, stress is proportional to strain. So elastic modulus, or E, is given by the formula stress over strain. This is still in Pascal unit. We also have the definition of deformation. Deformation refers to any changes in the shape or size of an object due to an applied force or a change in temperature. So for example, if it's too hot, or it's at boiling point, there will be some objects that will deform or will melt. So that is what we call the change in temperature. Deformation also alters the shape of a material upon the application of a force within its elastic limit. It is also the temporary change in length, volume, or shape produced in an elastic substance by a stress that is less than the elastic limit of the substance. This is the formula for the deformation due to tensile or compressive force. This is the pull or the force, no, or pull or the force, the push force. So we have this formula. This is the elongation or deformation. What you call that? The symbol. So you can just have that as this. That is equivalent to P times L over A times E, where P here is the applied force or the force, L is the length, A is the area, and E is the modulus of elasticity. So usually the units of this one is M or millimeter, meter or millimeter. So for the deformation due to change in temperature, we have this formula. Elongation or deformation is equivalent to lambda times L times the final temperature minus initial temperature. So T here is the temperature, L is affected length, and lambda is the thermal coefficient. We also have deformation due to self-weight. So we have deformation is equivalent to P times G, or the gravity, times length squared over 2E. So L is affected length, P is density, G is gravity, E is modulus of elasticity. So for example, we have a 30-meter long aluminum bar is subjected to a tensile stress of 172 megapascal. Elongation, find the elongation if E is 69,116 megapascal. So our L is 30 meter. Our tensile stress is 172 megapascal, and our E is 69,116 megapascal. We are looking for the elongation. So we are looking for this. Now, if you can recall, elongation due to tensile stress or compressive stress is equivalent to PL over AE, wherein P over A is just basically equivalent to stress, right? This is force over area. So that being said, if stress is already given, you can just multiply that stress times L over E. Since here we have already given stress, so we can just solve for the elongation by using the stress value. So we have 172 times 10 raised to 6 Pascal times the length, which is 30 meter, all over our our E, or elasticity of modulus of elasticity. So you have 69,116 times 10 raised to 6. So that is Pascal, Pascal, cancel the Pascal. So what we have left in the unit is meter. So this is equivalent to 0.075 meters. So this is now the elongation of our aluminum bar. Next example, and the last example, is a steel wire 10 meter long hanging vertically supports a tensile load of 2,000 Newton. Neglecting the weight of the wire, determine the required diameter if the stress is not to exceed 140 megapascal. Again, that is the stress. And the total elongation is not to exceed 5 millimeter. Assume E is equivalent to 200 gigapascal. So we are looking for two answers here: the diameter in the stress and the diameter in the elongation. So first, let's try to draw, or let's try to materialize what we are looking, what we are solving. So it says that we have a wire, and there is a weight hanging vertically. So the given, we have L is equal to 10 meter. We have tensile load with the force, which is 2,000 Newton. We also have the stress, which is 140 megapascal. We also have the elongation, which is 5 millimeter. And we also have our E, which is 200 gigapascal. So we are looking for the diameter for the stress and diameter for the elongation. So first, let's solve for the stress. We have F over A. We have values for F and we have values for the stress. So we can just interchange that. We have F over A, in which our F is 2,000 and our area is the area for the wire. So that's pi over 4 d, which is unknown, squared. Stress, I'm sorry, this should be stress, right? Let's just erase this one. It should be 140 times 10 raised to 6. And this one should be pi over 4. And we have d squared. So d here is basically equivalent to 4.26 times 10 raised to negative 3 m. That is the diameter for the stress. Now for the elongation or the deformation, we can use the formula stress. We can use the formula since we are looking for the diameter. We cannot use stress automatically, so we can have PL over AE. E. So elongation is given already. So we have 5 millimeter is equivalent to, can just change this into meter. P is 2000, L is 10. We'll be changing this millimeter into meter because we have given meter here for the length of our wire. For the area, we also have pi over 4 d squared times our E, which is 200 times 10 raised to 9 Pascal. So D here is just equivalent to 5.05 times 10 raised to negative 3 meter. So unlike in the weight, or unlike in the weight, we are looking for the smallest weight or smallest value for the weight. Now we are looking for the diameter to support the weight. We have to choose the bigger answer and the bigger value for the diameter so that it would have more capacity to support the weight. Okay, so I think that's it for this video. I hope you learned something from this video, and I'll see you on our sessions. Thank you, everyone.